Have you ever wondered how your computer can run multiple programs at once? Well, it's all thanks to something called a multi-program system, an ingenious concept that forms the backbone of modern operating systems. It's a computing environment where several programs can be loaded into memory and executed simultaneously. This idea is not only fundamental to our current digital age, but also crucial for efficient utilization of resources and improved system throughput. Let's delve a bit deeper. A multi-programmed system is characterized by several key aspects. The first one is concurrency, the ability for multiple programs to be in various stages of execution at the same time. Techniques such as time sharing and multi-programming make this possible. Next, there is memory management, where the operating system plays the role of a careful orchestrator, allocating memory space to each program and ensuring they don't encroach on each other's territory. Then we have CPU scheduling, a strategic process where the operating system decides the order in which programs get to use the CPU's precious processing time. This is where various scheduling algorithms come into play. Another aspect is the handling of input and output operations, often involving reading from files or interacting with devices. Here, the operating system ensures programs can execute concurrently without being blocked by these operations. Resource allocation is another key element, where the operating system shares system resources such as CPU time, memory, and I/O devices among the multiple programs. At the heart of a multi-programmed system is the concept of concurrency. Concurrency is the ability of a computer system to execute multiple tasks or processes simultaneously. So imagine you're listening to your favorite podcast while editing a document and checking your emails, all at the same time. This is concurrency in action. Now, you might ask, how does a computer with just one central processing unit manage to juggle all these tasks concurrently? Well, it's all about the illusion of parallelism. The CPU rapidly switches between tasks, spending a fraction of a second on each one. To us, it appears as if all tasks are running simultaneously. That's not all. The operating system also plays a significant role in this juggling act. It uses scheduling algorithms to decide which task gets the CPU's attention next and for how long. It's like a traffic controller, ensuring that each task gets its fair share of processing time. But what about memory? How does the system handle multiple programs loaded into memory at the same time? This is where memory management comes in. Memory management is a critical aspect of a multi-program system. It's the operating system's job to allocate memory to each program and ensure they do not overlap or interfere with each other. Think of memory as a giant storage room, with each program assigned its specific area. The operating system also has another crucial job: memory protection. It must ensure that one program cannot access or modify the memory area of another program. This protection is vital for the security and stability of the system. Additionally, memory management involves the use of techniques like paging and segmentation to efficiently manage and allocate memory. The operating system can also move programs that are not currently being executed from main memory to secondary memory, like your hard drive, to free up space. Effective memory management ensures that your computer runs smoothly, even with multiple programs loaded. It's a bit like a well-orchestrated symphony, each part playing in harmony with the others. It's one of the many marvels of modern computing. How does your computer decide which program gets its attention first? You may wonder. Well, this is where CPU scheduling comes into play. It's like a grand symphony, where the operating system acts as the conductor, deciding which program or instrument, if you will, gets to perform its piece first. And the music sheet, that's the scheduling algorithm. There are various types of scheduling algorithms, each with its unique way of determining the order of execution. For instance, the first-come, first-served algorithm is as straightforward as it sounds. The first program to request the CPU's attention gets it. Other algorithms, like the shortest job next or priority scheduling, use more complex criteria to decide the order of execution. Now, while the CPU is busy executing these programs, another critical operation is happening in parallel: the input-output, or I/O operations. These are essentially the ways in which a program interacts with the outside world. It could be reading from a file, writing to a screen, or communicating with a keyboard. The operating system manages these I/O operations in a way that allows for simultaneous execution of multiple programs. It does this by using I/O buffering, a technique that stores data temporarily while it is being transferred. This means that a program doesn't have to wait for an I/O operation to complete before moving on to the next task. it can simply continue with its other tasks, while the operating system takes care of the I/O operations in the background. And just like a skilled conductor who ensures each instrument gets its turn and that no single instrument dominates the performance, the operating system ensures fair and efficient use of the CPU and I/O resources. It manages the execution of multiple programs in a way that maximizes overall system throughput and maintains system responsiveness. So, your computer's operating system is like a skilled conductor, orchestrating multiple programs to work in harmony. And that's the beauty of a multi-programmed system. It's a symphony of simultaneous tasks all working together to create the seamless computing experience we enjoy every day. Your computer's resources are precious. How does it share them among multiple programs? Let's dive into this fascinating world of resource allocation and context switching, two key aspects of a multi-programmed system that keep your computer humming along smoothly. First, resource allocation. In a multi-programmed system, the operating system acts as a resource manager, juggling various system resources such as CPU time, memory, and input-output devices. It's like a master conductor leading an orchestra, ensuring each instrument plays at the right time to create a harmonious symphony. The operating system aims to maximize overall system throughput, or the amount of work done in a given time, and ensure fair resource allocation among competing programs. But how does it decide who gets what and when? This is where scheduling algorithms come in, helping to determine the order in which programs get access to the CPU's processing time. These algorithms might prioritize programs based on their needs, their importance, or even their behavior. Now let's switch gears to context switching, a process that's as dynamic as it sounds. Imagine a juggler tossing several balls in the air. Just like the juggler, the operating system must keep track of multiple programs, but instead of balls, it's juggling tasks. When the operating system switches from executing one program to another, it performs a context switch. This involves saving the state of the currently executing program, or context, and loading the state of the next program to be executed. It's like pausing a movie, changing the DVD, and then starting a new movie. Efficient context switching is crucial for maintaining system responsiveness and performance. It allows the operating system to manage multiple programs in a way that gives the illusion of simultaneous execution, even though only one program is executed at a time. In the grand scheme of a multi-programmed system, resource allocation and context switching play pivotal roles. They help ensure that your computer can handle multiple tasks efficiently, keeping your digital world spinning. Understanding context switching gives us insight into how our computer maintains its performance, even while juggling multiple tasks. In a world where data is king, how does a multi-programmed system keep your information secure? Well, it's all about protection and security mechanisms. In a multi-programmed environment, multiple programs are executing simultaneously, potentially accessing and modifying various data. To prevent unauthorized access or modification, the operating system implements robust security measures and access control mechanisms. Firstly, each program is isolated in its own memory area. This prevents programs from accidentally or maliciously interfering with each other's operation. This isolation is maintained by the operating system's memory management subsystem, which allocates and manages the memory areas for each program. Secondly, the operating system implements access control mechanisms to prevent unauthorized access to data. For instance, it may restrict access to certain files or devices based on user permissions. This ensures that only authorized programs can access and modify specific data. Lastly, the operating system can also implement security measures to protect against malicious software. For example, it can monitor programs for suspicious activity and block or terminate any programs that are found to be behaving maliciously. In addition to these protection and security measures, the operating system also plays a crucial role in managing resources, scheduling CPU time, and handling I/O operations, all while enabling the concurrent execution of multiple programs. To sum up, a multi-programmed system is a complex and sophisticated environment that allows for efficient resource utilization, high system throughput, and secure data processing. So we've covered the wonder of multi-programmed systems, the magic of concurrency and memory management, the art of CPU scheduling and I/O operations, the science of resource allocation and context switching, and the importance of protection and security. It's quite a lot to take in, but it's all part of the fascinating world of operating systems. So next time you switch between programs on your computer, remember the complex orchestration happening behind the scenes. Until next time, stay curious.